And here we are back with a recap of the entire first half of this course. So we share the screen. So we started with an introduction about the virtues of computer science, the power of abstraction, the importance of asymptotic efficiency, classes of asymptotic growth, like Ackermann function and inverse Ackermann function. And we discussed recalled and sorting as an example, where the importance of problem specification and the importance of problem algorithm optimality. Then we proceeded to chapter 2. No, you can see the slides. In chapter 2, we recalled some tree data structures. We recalled abstract data types as a way of hiding hardware and implementation details. We recalled basic data types and derived data types, and in particular linked data structures, particularly such as AVL trees, with the definition of an AVL tree, properties, quantitative properties of AVL trees, such as having logarithmic depth. We recall operations on our AVL trees and the maintenance of AVL property, namely the balance indicators and rebalancing operations, left rotation, right rotation, and double rotation. We analyzed the cost of these operations, and we ended with a deficiency, namely merging is something that AVL trees do not support in sublinear time, which led us to then consider binomial trees and binomial heaps as collections, as forests of binomial trees. We discussed the definition of binomial trees, two inductive definition, operations on binomial trees, maybe the merge operation, maintaining the heap order, and analysis, and then same definition of binomial heap, operations on binomial heaps, and we analyze these operations, and in particular we saw that all operations are now supported in logarithmic worst case cost. Thus, we have finally found efficient data implementation of the priority queue data type. Priority queue with emphasis on extract min, decrease key, and merge operation, which was one of the keys to Prim's algorithm. So from there, we would proceed to average case analysis. Average case analysis, first we discussed the purpose of algorithm analysis, namely to be able to predict the behavior of algorithms regardless of technical details such as clock frequency and other absolute measures, to predict it on the one hand realistically, and on the other hand to be able to analyze to make such predictions, which is a trade-off. The more realistic the prediction, the more involved the analysis. And for that purpose, we recalled various modes of algorithm analysis, such as worst case analysis and average case analysis. The topic of chapter 3, our motivation there was our worst case analysis of incrementing a binary counter, counting the number of bit flips, gave rise to significant overestimate. So as average case, we saw that 2 bit flips on average. Then we proceeded to our analysis of naive quicksort, which had a quadratic worst case running time, but we saw that on average, the running time is n log n, even without sophisticated pivot choosing algorithm. And we discussed the famous simplex algorithm, which even has a exponential worst case running time. But we saw, although we didn't prove it, that in smooth analysis, the simplex has polynomial runtime. Smooth analysis being, in a sense, a generalization of average case analysis to a continuous realm. That was chapter 3, and then chapter 4 on amortized analysis. Again, we started with a motivation of the binary counter, but mathematically the analysis was the same, but from a perspective of computer science, now we didn't consider an average input, but we considered kind of a sequence of increment operations and the average over the sequence of increment operations. And we were able to generalize that to a sequence of adding binary powers of 2, all resulting in constant amortized cost. Then we proceeded to discuss Fibonacci heaps, which are forests of relaxed binomial trees, which we had analyzed before in the worst case setting. And we saw that in the amortized setting, Fibonacci heaps have mostly constant amortized cost. And for that purpose, we would introduce and analyze them in terms of two savings accounts, which is one way of looking at the amortized cost definition and the analysis with a savings account. Only here we use two savings account, one to account for the number of relaxed binomial trees in the list comprising a Fibonacci heap, and another banking account to charge for the marks that are introduced whenever we turn a strict binomial tree into a relaxed binomial tree as part of the decrease key operation. Then we applied that amortized analysis to improve the worst case analysis of Prim's algorithm from Fibonacci heap to from binomial to Fibonacci heap, since Prim's algorithm does make a sequence of calls. That's exactly where the amortized analysis flourishes. And then we discussed Kruskal's algorithm also for minimum spanning tree, and saw that Kruskal algorithm builds on a disjoint set data structure. We discussed first disjoint set data structure, namely the union by weight heuristic, and we saw that the union by weight heuristic results in an amortized, logarithmic amortized cost. We also discussed fast and slowly growing functions, and what remains to show after the midterm is the definition and the analysis of the lazy union by rank heuristic with past compression, which turns out to have amortized cost equal to the inverse Ackermann function. So that was all we discussed, a lot of material we discussed in the first half of this course.